Hello, I'm Thomas Dawicki, and we are the Teledyne Optical Clarity Sensor Test Stand Capstone project, also known as Ultrapure Optics. I'm going to let the video take over for our introductions.
I'm Ayman.
I'm Katie.
I'm Thomas. And we are Ultrapure Optics.
For our capstone project, we are working with our sponsor, Vijaya and Teledyne Marine. Teledyne Marine specializes in the production of industry-leading subsea technologies used in oceanographic research, such as geophysical mapping and ocean observations. One of Teledyne's underwater vehicles, the Slocum Glider, is an autonomous undersea glider that utilizes the LISST-Tau sensor from Sequoia Scientific. The LISST-Tau is a laser-based sensor that measures water clarity measurements as the glider traverses through the ocean. Over time, the lenses on the sensor become cracked and require calibration verification. This is typically done by sending the LISST-Tau back to Sequoia to recalibrate the sensor. In order to simplify and speed up this process, we created a test stand that can verify the calibration by running clean water through the sensor. This test stand would reduce the downtime between Slocum Glider deployments by allowing clear water baseline readings to be taken on site.
In the design process, the team first researched water filtration and degassing methods. Contacts with the Sequoia Scientific also provided information on the operation of the sensor and the calibration process. Once this information had been gathered, the team was able to begin creating design concepts, functional models, and sketches. The team was able to evaluate each design and select which design best suited our needs. Calculations and simulations were performed on the chosen design to determine what components were needed. When our components began to arrive, individual component testing was conducted to verify our theoretical calculations. Finally, the full test stand was assembled and tested with the LISST-Tau sensors.
Our prototype solution is a portable closed-loop system that filters water before it's chambered through our LISST-Tau sensors. Tap water is supplied to the system's inlet, where it's run from the primary filter and a deionizer. The pre-filtered water is stored in the reservoir tank and is then fed into a pump which transports water upwards to be purified. Water then passes through the coarse membrane filtration line. This line can also be bypassed once water has been filtered repeatedly. Above this, our twin ultrafine polishing filters remove any remaining particles. A Gaster Module is used to remove any visible gas bubbles. This water is then channeled into a head tank, where an overflow line is used to maintain a constant height of water. Mounted to the stand are two LISST-Tau sensors, a laptop for data collection, and a display showing the flow rate of water into the sensors. This stream of water is controlled using a flow control valve. Water leaving the sensors is returned to the reservoir tank to be recycled.
Working on this project has allowed us to grow and learn about ourselves as engineers. Throughout the project, we were able to gain experience working as a team alongside our faculty advisors. This allowed us to hone our communication, expand our resources, and sharpen our analytical skills, transforming an idea into a tangible prototype.
Special thanks to Jesse DeRoches and the team at Sequoia Scientific, Wayne Slade and Thomas Lee for their help with the research of water clarity techniques. Additionally, thank you to Don Foster, Professor Vijaya, Chalivendra, Dr. Raymond and Professor Ayman for their help and guidance along the way. Without all your continued support, we would not have been able to accomplish all we were able to with this project.
Hey guys, I'm Ayman.
I'm Katie.
Okay, so for our project, our sponsor was Teledyne Marine, and our project manager was Jesse DeRocher. So Teledyne Marine is a company that specializes in a lot of different types of subsea technologies. These different technologies are used in oceanographic research, and what we're going to be focusing on is the water clarity readings that are collected from sensors that are deployed in the ocean. So the main purpose of this project is to create a mobile test stand that can perform very important clean water baseline calibration verification tests for the LISST-Tau optical sensors which are being deployed into the ocean. So these LISST-Tau sensors are developed by Sequoia Scientific, and they are mounted to Teledyne Slocum Gliders. So as these sensors are deployed into the ocean, they can become very easily fouled, especially due to how fine these sensor readings can be. So when these sensors are returned from deployment, they require calibration verification tests just to make sure that the baseline readings they're giving are still accurate. So typically these verification tests are performed by either sending the sensor back to Sequoia Scientific to be recalibrated, or they can be done in-house, but it requires disassembling the entire Slocum Glider, which can be a very lengthy and costly process. So in order to speed up and simplify this whole process, we developed a way to perform these clear water calibrations on site in a test stand that's very portable and easy to use. So a lot of background features were performed in order to begin this process. First, we contacted Sequoia Scientific, the manufacturers of the LISST-Tau sensor, and learned how they perform calibrations. They also gave us some insight in how to operate the sensor itself, and including the software that comes with it. So through this filtration research, we learned that the best methods that we can use are using a reionizer, a polishing filter, and a membrane gaster. Part of this water filtration research went into researching using a deionizer versus a reverse osmosis filtration unit, and we ultimately decided that a deionizer works best, both because of the guidance from Sequoia Scientific and because of our system overall. For the pump selection, we computed pressure drop calculations across each of our filters. These filters, especially some of our finer ones, can be damaged very easily if too much pressure is exposed to them. So this pump selection is very important. We developed a system equation curve in order to help us select the right pump for the job. And the safety standards, the most important thing we have to look out for is the interactions between water and our electrical components. So the main standard that we have to make sure we're following is that all portable lights or tools used in wet and conductive locations have to be protected by ground fault surface interrupters. So these components will be our main pump and our vacuum pump, our Arduino power supply, and the battery that's supplying power to the pump. So in order to help with some of this waterproofing, we use heat shrink around all.
That can cause clogging and pressure building. The pressure buildup can also damage components such as these filters or any of our lines in the system can blow. Then we had sensor failure. It wasn't something that we expected to happen, but if it did happen, it would be a pretty severe case. Water containing any bubbles. This would just negatively impact our results. Our water clarity readings would not be the water transmissivity would not be very high. Then we have water damage and leakage.
So to go through our test plan, we had 5 criteria that we really wanted to cover, starting with the actual head tank height. In our setup, we actually have our head tank pretty high up. This is to establish the actual flow that we want to go through our sensors. We experimented with having the head tank a little bit higher, a little bit lower, and we deemed that having it up high and having the sensors just a little bit lower on the actual posts that we have would give us enough room to actually generate that flow using gravity. Furthermore, we actually looked into moving the Gaster Module before and after the head tank. Using the degasser before the head tank allows us to actually use the pressure gradient across the filtration line and the pump to actually get the water degassed and pull vacuum on the actual degasser module. We weren't able to actually have the degasser module after the head tank and flow into the actual sensors. This would have been optimal to actually create 0 air bubbles going through the water into the sensors, but we would have to purchase another pump in order to create the actual flow. We also tested the gasser in an isolated environment to test how much gas we could get out of the water. We experimented using an oxygen meter that was a handheld device, and we could just filter or degas some of the water using the degasser module and measure the oxygen levels that were pretty low, around 48%. The oxygen levels within the water that were not degassed were around 75%. We also tested the pressure drop across the 0.2 micron polishing filters. The pressure drop across these filters was pretty high. We tested these using tap water, and this kind of actually led us into making a pretty important discovery, which was our porous filtration line, which functions to actually protect the polishing filters. The porous filtration line takes out any particulate matter that could potentially clog the filters, and we had to go back and actually figure out how to actually backflush these filters to mitigate the damage that could be possible. We also went forth and performed several cycles on the actual system without any electrical components connected besides the pump and battery to allow any leaks to expose themselves and to allow us to plug anything up that would cause water damage.
So as we finished up our final concept designs and test plans, we were then able to start pulling the components that we were actually wanting to use and put them in line with each other and get a good idea of what it would look like in the chassis and which components go where, and just start to formulate more of a test plan of, okay, we need to run these components in series because this is how they will be in the chassis, and just further develop the test plan. So as Ayman touched on, we got into our design testing. Since we had to do the pump calculations and the pressure drop, we had to start running our filtration line so that we could calculate the pressure drop and purchase the correct pump based on that. So before we could order our pump, we had to start with the individual component testing. And so as I mentioned, we did the filtration line testing with the degasser and the LISST-Tau sensor. A lot of these tests ended up working pretty interchangeably, and we ended up running most of them in line with each other with the LISST-Tau sensor to start to get a better idea of how exactly our system is going to work with the clarity readings. And then once our individual testing was complete, we were then able to start building our entire chassis because we had been able to order the pump that we needed and put the whole thing together and then start running the whole system as a whole. So just to go back through our design description, the chassis can really be broken down into 2 steps, the first being filtration and clarity. The water starts coming in from the tap source and into our initial carbon filter in the ionizing resin tank, where most of our sediment can be removed from the water. From there, it goes into the bottom storage tank and is then pumped up to our coarse filtration line with the 150, 65, and 20 micron filters, just to keep going down the line and filtering smaller and smaller particles without clogging our smallest filters, such as the twin polishing filters, which come after that coarse filtration line that filters out up to the 0.2 microns. And then out of the filters, we go through the degasser to remove any of those air bubbles, and then into our head tank. So from our head tank, we then start to utilize the gravity flow to pass the sensors. So we can use our flow control valve right out of the head tank to set our desired flow rate. And then the water will pass through our gold standard LISST-Tau sensor to get those baseline readings. And then to our valve LISST-Tau sensor, which is our device under test, to compare the 2 readings which are displayed on the laptop to get a good idea of how well the device that's returned from the glider is still functioning and whether or not it can go for another deployment or if it needs to be sent back to the manufacturer and recalibrated. And once it comes out of that valve LISST-Tau sensor, it goes through our flow meter just to verify the flow rate that's passing through the sensors is within that 2 to 4 liters per minute, and then it is returned to the bottom water storage tank to complete that closed loop.
So to basically look into how good of a process we could develop using the filtration line and degassing phase that we came up with, we looked into actually using the LISST-Tau sensors, comparing the values that we got of water clarity to the actual calibration data we were supplied with and are generated within the files that are created during actual data logging. So based on the current calibration to the clean water baseline, the actual values measure about 88.6% water clarity or light transmissivity. And these values are basically recorded by the sensor based on the actual scattering of the light beam across the actual lenses as it shoots through the water. The transmissivity of the water that we were able to generate going past the sensors actually kind of exceeded the clean water baseline and generated a transmissivity of 93.32%. These results were averaged over a range of 500 data points. but these over here are a small subset of the data we were looking into. So I'd say these results infer that sufficient water purity was created using the process we developed. So just to give and reiterate the actual importance of the actual constant flow rate we're looking for, in the data points you can see right here, the developed constant flow is actually pretty important as it allows the transmissivity values themselves to stay constant. One thing we experimented with was actually changing the flow rates between 2 and 4 liters per minute, which was the requirement across the sensors. And what we were able to achieve using a flow rate of about 3 liters per minute allowed us to actually give measurements that actually sat right within the benchmark of above 88.6 liters per minute, 88.6%. I would say that for more precision and more consistency within the data points, we would like to actually look into moving the Gaster Module after the head tank.
Okay, for our project schedule, we can summarize our progress across the 8 gates and then take those 8 gates and condense them into several sections. Between gates 1 and 2, we primarily focused on research and defining our sponsor's problem and how we plan to go about solving it. This involved researching about filtration, degassing, and the operation of the LISST-Tau sensor and how it works. Then during gate 3, we primarily worked on creating processes to solve the sponsor's problem using the information researched in gates 1 and 2. We created flow charts and sketches along with the process selection. Then in gates 4 to 5, we began to select components that corresponded to elements in the flow charts, along with purchasing when we had finally decided on components that fit our requirements. Then from gates 6 to 7, when parts finally began to start arriving, we moved on to component testing. A lot of this component testing involved determining the pressure drop across components such as our coarse filter line and our 0.2 micron filters and degassers. And then once all the parts had arrived, we were able to conclude with system assembly and testing in gates 7 to 8. When considering our budget, we used 80% of the $5,000 available. The largest budget item was in filtration and clarity, where we spent around $1,700. And for future recommendation, we recommend using paneling to conceal the exposed wiring. We also recommend replacing the bar connection filters with filters that the casing can be opened up and the filter cartridges inside can be replaced, which would make the maintenance on the system a lot easier. We would also recommend including pressure monitoring for the filters, which would allow it to signal to operators when filters should be replaced due to pressure buildup. We would also recommend incorporating ground fault circuit interrupters to protect electrical components and operators. Any questions?